well, each section we're going to do now is going to build on the last one. Tonight we're going to look at double angle and half angle identities, and we'll just notice that we can derive them from what we already have. This is actually important to know these proofs because it will help you when you forget these formulas. We're getting so many formulas they're going to be hard to remember. But we have this formula. Remember that the sine of alpha plus beta is sine cosine plus cosine sine. Right? What happens if we put alpha equals beta? We get, or let's say beta equals alpha, sine of 2 alpha is sine of alpha plus alpha. So you put beta equals alpha up here and you get sine alpha cosine alpha plus cosine alpha sine alpha. Well, there's 2 of those. What we have equivalently is that the sine of 2 alpha is equal to twice the sine of alpha times the cosine of alpha. So if you forget this one, you can prove it pretty easily from the sum identity for sine. Similarly, I think you should know the proof for this one. What is the cosine of alpha plus beta going to tell us? Remember, this one was cosine cosine minus sine sine. So there was the sum angle, sum formula for cosine. If we put beta equals alpha in this one, we get that the cosine of 2 alpha being cosine alpha plus alpha is, well, cosine cosine minus sine sine, each angle equal to alpha. So it's cosine alpha minus sine alpha sine alpha. Evidently, cosine 2 alpha is equal to the cosine squared of alpha minus the sine squared of alpha. Cosine 2 alpha is cosine squared minus sine squared. There's the double angle formulas for sine and cosine. Finally, we can do the same with the tangent. Remember the sum formula for tangent. Tangent alpha plus beta was tangent plus tangent over 1 minus tangent tangent, with the same sign on top plus and the opposite one on bottom. This implies putting alpha equals beta, the tangent of 2 alpha, the left side of beta equals alpha, is tangent plus tangent, is 2 tangent alpha, over 1 minus tangent tangent with the same angle is 1 minus tangent squared alpha. There's the formula for tangent. Let's put all those together now. What we have are these 3 formulas. Sine 2 alpha is 2 sine alpha cosine alpha. Cosine 2 alpha is cosine squared alpha minus sine squared alpha. Here I put theta. Tangent 2 theta is 2 tangent theta over 1 minus tangent squared theta. So we have these 3 formulas for double angle. Those can help us to do some new problems. Here's some example problems off of the UCO supplement. Suppose I wanted to calculate given that the cosine of theta is 2/3 with theta in the quadrant, in the second quadrant, suppose I want to find the tangent of 2 theta. How can I find tangent of 2 theta given the cosine of theta? Well, it turns out, remember, if you know one trig function in a quadrant, you know all 6 trig functions. So I can use this one to find tangent in particular, and then the tangent of 2 theta formula will allow me to evaluate the tangent of 2 theta. So here's what we do. We first, from cosine theta equals 2/3, and theta in quadrant 2, we can compute the sine. The sine, for instance, can be calculated as plus or minus the square root of 1 minus the cosine squared. We would call from the Pythagorean identity solve for sine is plus or minus the square root of 1 minus 2/3 squared is 9/9 minus 4/9 is square root of 5/9, or plus or minus is plus or minus the square root of 5/3. Now as a plus or minus, that's where the quadrant comes in, right? In quadrant 2, we remember that sine is positive and cosine is negative, so it must be that we want negative for quadrant 2. That computes sine of theta. Now, tangent of theta is sine over cosine. It has to be minus the square root 5/3 for sine, 2/3 for cosine, and we get minus the square root of 5/2. There's the tangent of theta. Now finally, by the double angle formula, we'll say that the tangent of 2 theta is 2 tangent of theta over 1 minus tangent tangent, 1 minus tangent squared theta, was the double angle formula, is minus the square root of 5 is twice the tangent of theta, over 1 minus tangent squared is 1 minus 5/4. Well, 1 minus 5/4 is minus 1/4, so this is minus the square root of 5 over minus 1/4. And we wind up with 4 square root 5 for the value of the tangent of 2 theta. Here's another problem. Suppose I want to simplify an expression. Oops. This comes up fairly often in actual practice. Suppose I want to simplify 2 sine pi/4 to cosine pi/4. How can I do that? The object is to recognize that it looks like something you've seen before. What does that look like? 2 sine cosine looks like a double angle identity. So let's call this twice 2 sine pi/4 cosine pi/4. And, alright, 2 sine alpha cosine alpha was sine of 2 alpha. So this is sine of, and in here goes 2 alpha, so that's 2 times pi/4. Now what we have is twice the sine of pi/2. Now we can also evaluate this and say, oh, sine of pi/2 is 1 and this is 2. But I just said simplify, so I'll simplify it to here. You could have done this with some other angle besides pi/4. Here's another one. Suppose I have this triangle and I have alpha sitting in here. What's the cosine of twice that angle? Well, we have a double angle formula that says this is cosine squared alpha minus sine squared alpha. So if I can just find sine and cosine out of that triangle, then I'm set. Well, I can, because with two sides of a right triangle, I should have put that in there. The last side has to be the root sum square of the legs. Hypotenuse does. This is actually comes out to be square root of 169, which is 13 then. So the last side is 13. I notice the cosine then is the adjacent side to alpha over the hypotenuse is 5 thirteenths. The sine is the opposite side to alpha over the hypotenuse, 12 over 13. So I wind up with 25 over 169 minus 144 over 169. And I get minus 119 over 169 is the exact value of the cosine of twice the angle shown.